Welcome to the Structural Intelligence Podcast, the show where we explore the intersection of engineering, technology, and innovation. I'm your host, Owen Keenan, structural engineer, entrepreneur, and tech enthusiast. Each episode brings together innovators, experts, and thought leaders who are pushing the boundaries of what's possible in engineering and technology. Through deep conversations and practical insights, we explore how new tools, techniques, and mindsets are reshaping our industry. We hope you enjoy this episode. All right, welcome to the Structural Intelligence Podcast, the show where we explore the intersection of engineering, tech, and innovation. I'm your host, Owen Keenan, and I'm a structural engineer, entrepreneur, and tech enthusiast. Today's episode is a fascinating one. We're diving into the topic which blends real-world risk, legacy standards, and computational breakthroughs at the center of one of the most foremost experts in maritime engineering. So joining me is Jordan Butler. So Jordan is a senior structural and maritime engineer from WGA, but he's also chairman of the PIANC committee, which is a working group 251, which is about the snapbacks and other things, which we'll talk about soon. Jordan has a unique design experience and cutting-edge expertise in the computational modeling of mooring line snapback failure, a topic that's not only technical, but critical to safety and engineering risk management at ports all over the world. So today we're going to be unpacking three big themes: the history and evolution of snapback analysis, how engineering standards are coping with or even lagging behind maybe some of the changes that are happening in modern technology, but how data is really reshaping the way that we think about design and uncertainty. So Jordan, welcome to the show. It's great to have you here.
Thank you.
So I've gone through a little bit of the background, but I'd love to hear in your own words, I guess, your journey and sort of your background.
Yeah, so my journey to engineering, I think, was atypical. When I was a young boy, I wanted to be a musician, wanted to be a rock star. So I studied guitar, and life took a few turns there for a bit. By age 14, I was living in Port Hedland, but actually I was homeless, and I was in a youth hostel. But I kept studying guitar. I worked 3 part-time jobs, and by 16, I was able to move down to Perth. I got a scholarship to John Curtin College of the Arts for guitar. Rented myself a room and was able to continue on my my journey towards being a successful musician.
Do you still play now?
I do, yeah.
Cool.
I've got a couple of guitars set up in the office, actually, much to everyone else's dismay.
Actually, I've seen them. Yeah. They're great. Yeah.
But I remember my music teacher, Miss Sheridan, she thought I was terrible because she gave me the advice, just go do something related to mining. I don't think music is for you. And in the short to medium term, I kind of showed her because I got to Whopper and a bunch of her other students didn't. So I thought, well, joke's on you.
There you go. Hey, yeah.
But I didn't actually stay in Whopper all that long. I did a year, and I was already working in music. I was teaching. I was doing sound and audio. I was composing for film and video games. And I thought, if I'm already doing the work, why hang around to do the degree? So I worked in music for about 7 years. And I guess I don't want to call it an epiphany. It's something that developed over time. But I realized that my bread and butter was teaching, and at teaching, you operate at the level of the student primarily. You're going over the basics over and over again, and it just wasn't pushing me. I wasn't challenged. So I decided, look, I'm just going to change field. I'm going to pursue something that just engages my brain and drives that or satisfies that itch, I guess.
That's where you jumped into engineering, I suppose.
Yeah. Look, I weighed it up against medicine, which was twice as long in uni, and I said, that doesn't sound great. So I picked engineering, and engineering was a great choice. I mean, across my studies, I worked in 3 countries. I was in Australia, China twice, and Japan for all of my prac work. And I graduated. I worked with ACOM in the Ports and Marine team for a few years. I was heavily involved in Engineers Australia. It's actually where you and I met.
Yeah, that's right. Yeah,
Young Engineers Australia Committee, which I went on to be the national chair of. And it was kind of through that process that I realized that I wanted to gravitate to something that was a little bit more focused on the industry that I worked in. So around the same time I changed company, I joined WGA, also in their Ports and Marine team. And I quickly found myself working on problems that were outside of the remit of the codes and standards. There wasn't a clear-cut answer. And that was just my space. I loved it.
That's interesting. Interesting with your background, you say it's atypical. You come from, typically, you go through like school or you come through uni and then, I want to do engineering. You jump in, you fall into it and then you get into it. But here you come from maybe a more creative type of thinking background, which I guess a lot of engineers wouldn't have. I suppose from what you've just said to me, that's quite an interesting origin story for you. And maybe some of the problems that you're thinking about now are influenced by that. So I don't know. Continue.
I guess, look, even though I work in the ports and marine sector, the way I describe my job right now is I'm a professional problem solver. And that's really exactly what I want to be doing. I don't want to be religiously following thou shall do this, thou shall do that, and just printing designs. I want to be solving problems. And one of the problems that I came across pretty early on, and I've been working on it, I'd say, for 4 or 5 years now, is mooring line snapback. What happens when mooring lines break? Where do they go? How do you stop them? And this wasn't a case of just follow the guidelines, and when they don't work, then start to think about the problem. Right. There were no guidelines. So at that time, I was starting to get quite involved with PIANC, which is the World Association for Waterborne Transport Infrastructure. It's not even close to the acronym PIANC. And I
wrote like ships and vessels and ports and that sort of stuff.
Inland waterways as well. There's an environmental arm, but essentially it's the world body for everything to do with port guidelines and standards. So I wrote the terms of reference to assemble a new working group, which was to address the problem of mooring line snapback because there was no guidance on it. I was appointed chair for that working group.
That's great.
In parallel, WGA supported me and I started to formalize my research. I'm now doing a PhD with Swinburne University at the same time and continuing to work on maritime projects.
That's an interesting thing. And I think what we're going to do in this podcast is dive a little bit deeper into that, dig down and get some of the learnings that you've got from, number one, working on problems that I suppose are more complex and have different elements that aren't just X, Y equals Z, So with the snapback mooring, I'd love to dive deep into a little bit of your working group stuff. But for the audience, and as we dive into it, just to give us a bit of context, what is snapback analysis? And what are mooring lines and how does that work? And I suppose that will sort of set the scene for our high level discussion later, which we'll have about design standards and data and how that really drives and influences and how we're using that as more of an innovation thing as opposed to the status quo. But if you can, in simple terms.
Yep. Look, I thought this question had come up, so I came prepared.
That's it.
A mooring line is a elastic, typically synthetic, high tensile rope, and it's used to arrest the motion of vessels when they're alongside berth. As for what snapback is, it's the event where a mooring line breaks. But I thought it'd be better to show rather than tell. So Trelleborg actually gave me a little model of a bollard itself. So
that's like a mini model version.
So this is about the worst possible braided synthetic line I could make, but I did make one. So a snapback event is essentially I've got a mooring line under tension, high elasticity, a lot of stored energy, attached to a bollard at the deck. The vessel's motion introduces friction and wear on this point of redirection up at the side of the hull. And under a combination of load and that damage, the line fails and you get that. Snapback is that, but at the scale of a line that's the size of my forearm, moving at the speed of sound.
A lot of energy in that as well. Huge.
Unbelievable. And the time domain element of it is so fast.
And I suppose not only, I guess, designing for those sorts of things, but the risk associated with snapback from a health and safety risk, and also I can imagine this potential energy that's released, is catastrophic.
Yeah, absolutely, and frequently fatal. Look, our best estimates are that there's a snapback event at a port somewhere around the world once every 8 minutes.
Yeah, wow.
The data that we have from the UK suggests that for every interaction of a parted mooring line and a human, 1 in 7 of those events results in a fatality.
Yep.
In Australia, we have about 1 fatality every 5 years or so.
Mm-hmm.
For other countries that are tracking data on this, it's as frequently as every 2 years.
Yeah, wow.
And there are entire continents where we don't have reliable data at all. So it could be significantly worse than we think it is, but there are gaps in the data.
And this is an interesting point, right? Where you've got a complex system of a mooring line and a snapback and velocities and motions and other things like that. You've got different elements, I suppose, in play there, where it's an uncertain system. It's not a system that can be solved directly by sort of one thing. You might need a lot, and we'll talk about that later. But what are some of the, I guess, typical scenarios that would lead to a snapback failure?
Yeah, so this really is a big part of the challenge that the working group has to deal with, but also every single port operator, asset owner, any person who sets foot in a port environment needs to consider in the context of that location because it changes. It's frequently the case that lines fail due to line condition, that they simply wear, friction, heat, all of these problems cause them to break. But there are a bunch of other considerations that vary from site to site. Some facilities that we have in Australia, for instance, are exposed to long period waves, so extremely long waves, very low height, but a lot of momentum in them. They're able to move a vessel up and down the key line, and you practically can't see them coming. And that massive displacement of the vessel on usually a single line that's restraining it can cause that line to break. Mm-hmm. There are other cases where some of our ports have extremely large tidal ranges, and the change of the elevation of the vessel itself through the loading of bulk materials causes the line angles to change drastically across the course of a day. So you could see the elevation of the line move by 20 meters. And so perhaps when it comes into berth first secured, everything's fine. But through the course of the day, through the course of these changes that are happening, we're introducing new points of redirections with infrastructure that's berth side, or there's line handling issues where the winches aren't paying out properly, which allows the vessel to move. And all of these factors can contribute to failure. And then the challenge after that is you say, well,
where does it go?
Where does it go? But also, like, at what load does it fail?
Yeah, what load does it fail? Yeah.
There are proposals for systems that would alert you that if you're over tension, but what we found so far is that the median event happens at about 30% of the mooring line's capacity, so significantly lower than what the line was designed for. The problem is that a brand new line will achieve that load every day of the week and be happy. So should you continually shut down a port on false negatives? Or how do you deal with these events, these low tension events? They still pose a risk to personnel, but very difficult to forecast.
Interesting. So you've got condition, you've got different environmental elements with tides and things like that, different arrangements with, say, the vessels and how they're loaded and things like that. So you've got a lot of moving parts. You've got a complex system.
Yes.
So design then. So you're thinking about, what are the conditions and how do I do this? And because there's so many variables, I suppose it's difficult to compute that, I suppose. But can you take us back through, I guess, the current standards that we've got now? I guess some of the early guidance around snapback and how to quantify that risk and how it was dealt with before. And then potentially thinking about maybe moving on from there. But if you can just give us some of that context, and I think we talked a bit about a failure that happened in 2015 as well. That sort of sparked off a few different changes to that original thing. So if you can sort of work us through that. That'd be interesting. So.
Snapback research begins primarily in the 1960s.
Yep.
And prior to that, it's a combination of synthetic lines don't exist yet or aren't in use. So these high elastic lines that store a lot of energy aren't present in ports, and vessels are substantially smaller. The combination of those two things means that even if lines did break, they typically didn't recoil. But in the 60s was about when that started to change. The US Coast Guard, and there was some research being done out of Stuttgart in Germany, started to look into what was going on with these lines. The US military in particular said, we've got cases of people getting cut in half by mooring lines now. We need to solve this problem. All of their initial work was focused primarily on how fast do these lines go, and they were typically producing values of 200 to 250 meters a second, so about 750 kilometers an hour. And then subsequently, by the time you got to about the 80s, they started saying, okay, well, what can we do in terms of the material composition of mooring lines to reduce the recoil properties? And they started looking at Kevlar, and then Dyneema is another line type that showed up thereafter, which are lower stretch lines, store less energy. None of this really showed up in the guidelines period. But what did show up was 1992, the OCIMF, so that's the Oil Companies International Marine Forum, published Mooring Equipment Guidelines, Volume 1. And it was an interesting document because it was somewhat prophetic in a sense that they knew that there was a lot more work that needed to be done. And there's this exceptional quote that's at the front of the document, and I had to write it down. I don't quite have it memorized, but perhaps I should, because I think it's possibly one of the most important lines I've ever read in any guideline.
Sure.
And it says, these guidelines represent a recommended minimum requirement. They're not intended to inhibit innovation or future technological advances.
Wow.
So they understood, hey, this problem's not solved. And there was a lot of other stuff in mooring equipment guidelines as well. But what they did show is these things that have been referred to in industry as snapback cones. And they were these graphical representations based off of about one paragraph of text in this document that says, if a line recoils along its own length, it can move anywhere about plus or minus 10 degrees from its idealized position. If it's redirected, it can whip and the paths become more exotic.
Yeah, right. So that's sort of like a failure cone.
Exactly.
And anyone in that is at risk of getting hit. Essentially.
Now, the challenge there was that mooring equipment guidelines advice is primarily for vessel-side infrastructure. And all of the mooring infrastructure on a vessel doesn't move with respect to itself. So the winch is always the same distance from the fair lead. And so everything's a little bit more predictable. All the lengths and stuff that you have to deal with are predictable. But over on the facility side, port side engineers, they started adopting these snapback cones as well, even though vessels move, mooring arrangements change. There are all of these, the failure point could change, and tides, loading conditions, all of these things that we talked about previously, they all have an influence on snapback path. But through edition 2 and edition 3 of mooring equipment guidelines, there wasn't really a change. That brings us up to 2008. 2015, as you said, there was the Zagar incident. So Zagar was this vessel, I believe it was berthed in the UK at the time. And it was using high modulus lines, kind of off the back of what I was talking about with the US research about how do you make lines less elastic.
Yeah, that's right.
There was a false sense of security because they were using these low elasticity lines that if the lines don't stretch, the lines don't store energy, and therefore snapback's not a risk. But the original idea of elasticity in lines is to allow a vessel to move without it being these instantaneous transient loads that really spike loads into one line and cause failures in the first place. And they started to get around that by attaching tails that use nylon or polypropylene. And this mooring line in particular had a 22-meter length of, I believe it was a poly blend tail on it. That length of line had all the elongation and all the stored energy that it needed to generate a snapback event. And so the line did fail in the high modulus part, the other material. But with all this stored energy, it was able to whip around the deck of the vessel, go off over the side of the hull, wrap around the vessel, and then come back and strike a person on board the vessel on the opposite side of the fairlead to where the mooring infrastructure was. The person was airlifted out. I believe they survived. But it triggered this investigation. And it was the first time, it was OCIMF with the support of others, it was the first time that we've got written history for where direct computational analysis of a snapback event was undertaken. And they're able to reproduce the event. They produced velocities again in the order of 250 meters a second, which is consistent with the physical testing that had happened decades prior. And the simulation showed more or less the same failure event. It went off the side of the vessel, whipped back around, came back on vessel, and hit the same location.
And was that in the cone of failure? That
Not even close. No.
So the guidance at that time, it sort of was, I guess, showed a different scenario to what was expected, or at least in the cone of failure, which I assume had some sort of a fat in that, or some variances. So
it's really difficult to pin down precisely where the failure cone guidance originated from. There's some writing about it where they've shown diagrams and they seem to be talking about the buckled shape of the mooring line as it compresses and it buckles, how it widens out. But it didn't seem to consider the variability that we talked about, that failure points could happen at all these different locations that vessels move, and all of the interactions that happen after the line is in motion, which is what happened in the Zagar case, is that it was able to wrap around a fairlead and then come back as a result, which is this secondary effect that no one had ever considered until it was modeled. So Mooring Equipment Guidelines 4th edition was published in 2018, and it got rid of everything in terms of snapback cones. All the diagrams are gone. The guidance simply says consider everywhere to be a snapback risk.
And that's quite onerous, I suppose.
It is, It's exceptionally onerous if you want to think about the operational constraints that puts on a port or a vessel.
So just jumping into that then. So you said that they did some computational analysis.
Yes.
And I know that that's something that you have sort of jumped into and maybe extended that part of the research, or and done some work on that. And this is what I really wanted to get to the nuts and bolts of, which is, okay, we have some guidance, we know the history, we know where it's come from, and we've seen different incidents around it. But now there's a path forward which we didn't have before, which was computational analysis that we have now. Can you give us a bit of a description or a background of what you've done in terms of modeling this snapback and the process of which that's completed, but also maybe some of the outcomes from that, and some of the learnings and some of the key points that you're like, oh, that's actually a realization now. We can sort of do that.
Yeah. So it's important to consider it in the context of when I enter the scene of assessing this problem. So the 4th edition of Mooring Equipment Guidelines is already published. It says everywhere as a snapback zone. Not every port, in fact, the vast majority of them, has responded to that guidance and updated. They're still using snapback cones at the time. And snapback events are still happening all around the country, all around the world. And every so often, events happen where the line goes somewhere that people don't expect, and it triggers this big inquiry into it. That was kind of where my involvement started. There was an event with BHP Hay Point over in Queensland, and WGA and others were asked to look into that event.
Yeah, sure.
I started really focusing in on how do you model the path of a parted mooring line. What's the underlying physics and kinematics that are going on here? And I did this without knowledge that the modeling of the 2015 Zagar event actually existed.
So it was kind of, there you go.
Developed independently.
Yeah, that's right.
But I think the thing that was particularly different between my mentality going into looking at the BHP incident and the Zagar incident is just there's a half decade of computational advancement between those 2 points. So for them, I imagine it wasn't even possible to consider what does this look like at scale. And for me, it was. I said, okay, well, I don't need to model a single event. I can model 100,000 events. I can model 1,000,000 events.
Yeah.
Right? We can get the computational time down such that we can run through all of the possible permutations of different breaking points and different vessel motions and different configurations.
Yeah.
And the result from that was being able to create these, it's hard to describe it. Essentially, it's data in three-dimensional space that's almost a heat map of where are all of the possible locations that a mooring line can go.
Wow. So you basically ran a probabilistic,
yes,
different and varying the factors that we talked about before to produce basically an envelope of what the possibilities of this mooring line could go and where it could go. Would that be correct?
Yeah, exactly. Yeah. And so we did a lot of work on, there was a lot of work on how do you model the failure of a mooring line? How do shock waves move through it? How do the different parts of it get accelerated at different parts in the time domain? Because these events are so fast that parts of the mooring line still behave as if they're in tension while other parts are moving because the shock wave is propagating down the line. And we did a bunch of work on how do you grab this data, which, say, for a facility might be in the order of 20 terabytes of raw data that we'd compute. And how do you encapsulate that in a way that's visually interrogable by a user? And it somewhat approximates a snapback cone or a snapback path in the end.
Yeah.
It doesn't necessarily look like a cone anymore, but now it's a probabilistically modeled version of the snapback cone, which says, here's the envelope of all of the possible paths that we calculated. But more importantly, because it's not a single data point, just apply a cone, because it's the envelope of cases, you can take subsets of that. You can say, all right, I'm particularly interested in what happens when it fails at the fairlead instead of the winch. I'm particularly interested in what happens when the vessel is at high tide in a ballast condition. I'm particularly interested when the breastline is attached to this dolphin rather than that dolphin. And the reason why that's important from a port operations standpoint is that allows them to make decisions about what's actually happening at their facility rather than the blanket statement of the entire port is a snapback zone. That may well be true if you assessed every possible permutation of every possible line in every possible condition, but not all of them are true at the same time. And so by generating these massive databases of snapback paths and enveloping them and having these subsets, we can dynamically update what is a snapback zone for the given conditions at the time.
So we're moving from what I can see in this application anyway, is we're moving from what was a rule of thumb and understanding of a component of risk and then adding a factor on top of that or whatever it is for a risk-based design decision to we've got the data, or we can probabilistically compute every single scenario or at least 99% of the scenarios because of the current compute that we've got now to make better data-driven decisions. Would you say that is the contrast that we're having now and so I guess the transition that we're having?
Yeah, I think that there's a certain degree of nuance in that probabilistic-based design isn't necessarily a new concept. But we're now at a point with computation where the data to drive probabilistic design can be undertaken by the design engineer.
Yep.
If we step back just one decade, right, we are in a situation where probabilistic models still existed, but it was the aggregate of recorded data from sites around the world for whatever condition you were looking at. An example might be our wind code and its different regions. Another example in maritime could be the berthing velocity of vessels. But in this case, the data is generated by the engineer themselves looking at the particular facility that they're looking at. So we get to take probabilistic design and hone it down into I think the most fit for purpose version of it, which is on a per facility basis.
Yeah, right. Yeah.
The challenge that I have with deterministic design is when it gets put up in contrast as probabilistic design, it's kind of just moving the goalposts a little bit, but it's still probabilistic. It's just someone did the legwork before you and they put a number to it and engineers just adopt the number.
So they codified the standards from standard practice and previous empirical testing and stuff
like exactly.
that, where you can get an answer.
You design a steel structure and you adopt your yield stress as 350 MPa. Well, it's not 350. It's a probabilistic distribution of possible yield stresses, and that might be the 5th percentile of all cases that you're going to adopt for design. I think in the world of maritime, we're a lot more comfortable with probabilistic design because it's necessary, because the conditions of every site are so different, and because we've been doing it for so long that it's kind of, to a certain degree, entrenched in maritime standards. If we go back to the 1940s as an example, Operation Overlord, which is the code name for the Allies landing at Normandy in World War II, that was an exceptional feat of maritime engineering, which is one of the things that gets overlooked. Is in order to land at Normandy, you have to be able to calculate the tide. You have to know when the tide is going to be out far enough that you can land on the beaches and clear defenses, when the tide is going to run in far enough that vessels can come in and you can get the troops as close to the gunning points as possible and reduce their risk. It was Lord Kelvin's brass harmonic machines that they were using to calculate this, but they needed site data, and they were sending divers in the cover of night to the coast of France to record data at the site, bring it back to calibrate this Fourier transform that they were doing to say, okay, the tides will be this on these days. Yeah. That's a perfect example of local data, probabilistic modeling, and saying, all right, the tides are going to do
making a design decision, I suppose. Yeah.
You know, you jump forward to the modern day and we take for granted that we can get that data for anywhere. I know exactly what the tides are going to be. I know what the significant wave heights will be. I know what the periods are. And the design standards are written as such. They say, okay, well, you're going to design for H max, H 0.4, H significant. These are different statistical exceedances of wave height. It doesn't tell you what that wave height is. You have to then go and get the local data to make that decision. So for that to move over to say something like mooring lines or anything of the sort, it's not that big a jump in the world of maritime. It's kind of how we've been engineering for a long time. I think what technology does, which is the real differentiator, is you don't have to rely on third-party data anymore. You're able to make direct computations, produce your own data sets for your own sites, and then make more targeted decisions about what's driving that site.
So what I can see is, like, with the data, we can actually get, rather than putting a blanket over, okay, this is the empirical testing, the codes that have been done, and we're trying to capture a subset or a superset of everybody, you know, but we can, with the data, design to our site as well. So that's quite an interesting thing. What I really want to talk about now at a bit more of a higher level is that engineering mindset in terms of that probabilistic design, deterministic design, but just the paradigm shift of, okay, we actually understand now, we have the tools at our disposal to do these sorts of things. One application was snapback failure. So extrapolating that a little bit, and for our engineers listening, right, is how do we really harness that methodology, something that you've sort of thought about, the thinking behind it. How do we harness that for other applications? You know, we do bridge designs, building designs, or whatever it is. But how can we do that, do you think?
It's challenging because we all operate within a larger ecosystem that's driven by client demands, driven by reviews, driven by standards. And for as long as it's the case that standards say thou shalt design to these particular values, it becomes very hard to get away with that and get away from that, I should say, which is why I pointed to that quote from Mooring Equipment's Guideline 1, which is, this should not be considered a substitute for future innovation. And I think that that's an incredibly important mindset to have in any engineering operation, is to say, okay, the guidelines say this, but at the time the guidelines were written, this is the hand they were dealt. Take stock of your own situation and say, is that the hand that I'm dealt? Or if something has changed, what has changed? And how can I capitalize on that to drive either more efficient or more informed engineering design? And big part of that, I believe, moving forward is going to be capturing data.
Yep.
And we have the ability now. And I think that really is one of the key differentiators, is that our accessibility to data is unbelievable compared to even, say, 1 decade ago. And that would be true of bridges, of roads, of buildings, of any structure you could imagine. You take an example of your wind codes that we talked about before. Can you capture the wind data for a particular site? Of course you can.
Yep.
Can you do Monte Carlo simulations to show 500 years of storm tracks over that site to show what are the actual conditions for it? Yep, you can do that as well. Could you calculate what the aerodynamic roughness of your site is so you get the particular terrain category that you need rather than just it's 2, it's 3? Can do that as well. But that would require going beyond what 1170 is going to tell you to do and starting to make really informed decisions with really good site data, which requires a bit of courage as well to actually do the work, get the data, and vet the data as well, not have blind confidence in it to use it as a substitute.
And it comes back to the start of the podcast where you talked about I'm a problem solver, you know, and you started to, when you came to the realization that you wanted to extend yourself and do those things where this is an example that there are a set of guidelines, set of standards, but you've moved beyond that because of your thinking to something that is what a real engineer or someone that's really thinking about the design of it needs to think about, I'd say.
High praise. Thank you.
Yeah, no, I commend you for that, because I think as engineers, we should really be able to push the boundaries or push the limits of what is possible with the technology that we have. And that's not to say we're going to be, I suppose, reckless with it, but we really need to think about, okay, we actually have the tools at our disposal now, more than we ever have in previous times. So as we wrap up, I just want to hand over again to the ChatGPT or AI host. He's going to ask you a question. He's going to close it out. And then we can say a couple of final words, if that's all right.
Sure.
So we can jump into it. I'll now hand over to the AI host.
Sometimes the hardest thing to change is what we've always believed to be true. Today, we explored how modern tools like high-volume simulations are transforming our understanding of risk, challenging legacy assumptions around Snapback, and reshaping engineering standards. Jordan, you've shown us how data is moving us from conservatism to clarity. If we now have the power to model the unknown, how should that reshape what we accept, assume, or design for?
It's quite a profound question, Mr. AI.
Absolutely, Jordan.
The truth of the matter is that there was always residual risk in design standards. When we made the changes in the industry to ULS-based design, that was based on statistical exceedance of design events, statistical exceedance of the characteristic material properties and the joint probability of those two things. The question we have to ask ourselves now is, if we are able to parametrically model all of the possible permutations, should we be adopting a singular design value, or should it be the case that we look at the entire spectrum of possible loads, the entire spectrum of possible responses, and we calculate what that residual risk is ourselves? I think to a lot of people in our industry, that's scary because it quantifies where the failures can happen. But as an engineer, I see that as an opportunity. That tells me, is there a repeated theme that predicts this type of failure? Is there some kind of control that I can start to think about? Because rather than abstracting it into the way it was done in historical ULS design, I now have 200,000, 300,000 design cases where I can look in and say, okay, 100 of these, there was an issue. What was the issue? Do we accept the issue? How do we control the issue? We start to make data-based decisions. And that's a future that I welcome because it's more informed and we will make far more considered design decisions. And the people that will use these facilities for decades to come will be able to look back and understand what are the consequences of failure, where does the risk lie, which is far more visible with this kind of data than it ever would have been in the past.
Absolutely. It's a shift toward more considered, data-driven design decisions, making engineering not only more efficient, but also more transparent. If this episode sparked something, stay with us. We're just getting started. In future episodes, we'll keep unpacking what modern engineering really looks like, not just on paper, but in practice.
I'll look forward to it. Thank you, Mr. AI.
That's it, eh? No, that's great. Really enjoyed the time. Did you have any final words?
No, other than, I guess, going back to that mooring equipment
please.
Guidelines, prophetic statement of don't allow the guideline to inhibit future innovation. Don't allow this conversation to inhibit future innovation. I'm sure over the next decade, people will look back to the conversation that we've had and say, for 200,000 permutations. That's a bit cute, isn't it?
Yeah, that's right.
So, go forward, innovate, challenge, and be a professional problem solver.
Great. Thank you again, Jordan.
Thank you very much.
Yeah, it's been a pleasure. So again, my name's Owen Keenan. This is the Structural Intelligence Podcast, and we hope you enjoy listening. Follow us on LinkedIn, also YouTube, Spotify, anywhere you get your podcasts. And it's been great to be together and have this conversation today. So
it's a pleasure. Thank you.